Welcome back to Math 107, College Algebra. In this video, we're going to take a look at the fundamental theorem of algebra and a key consequence of it. So the fundamental theorem of algebra says if we let f of x be a non-constant polynomial, then there exists a z within the complex numbers such that f of z is equal to 0. This is true for any non-constant polynomial. So what's important here is if we take a generic polynomial, so I'm going to use p of x here, well, it has to have a 0, which by the factor theorem that we talked about in class on Monday means x minus z is a factor of that, so we know p of x has to equal x minus z times q1. Actually, I'm going to call this qn minus 1. Of x. We're going to use that n minus 1 to indicate what the highest power in the polynomial is. Well, qn, or q sub n minus 1 of x, is a polynomial. It's not constant. So we can do the same thing again. And then this time we'll use a different letter. We'll say x minus w times q sub n minus 2 of x. Well, we keep on going with this. Eventually this whole process is going to terminate. So we can say p of x is equal to, and I'm going to switch to calling all of these zeros alpha. So we can say p of x is equal to some constant, which we'll just call a, and then x minus alpha 1 times x minus alpha 2, and so on, all the way up to x minus alpha n. And we will say alpha I is some complex number. A also is going to be some complex number, although for the stuff we'll be working at, we're usually going to assume it's a rational number. And the further thing we have here is that this factorization that I've shown here is going to be unique down to I could reorder these. So we'll call that factorization unique up to order. And I will point out these alpha i's are not necessarily going to be distinct. We could have, say, 3 different numbers that alpha I is 1. But we are always going to have n of them, up to the fact that we could have some repeated. So that's the fundamental theorem of algebra, and an important consequence of it In the next video, we're going to take a look at how we can actually factor an arbitrary polynomial.